Way early coffee morning here, folks. Good one, though. So, I got up wondering how I could explain zero, or how someone could explain zero, right? So, zero is nothing. It's a concept, it's an idea. If you were a computer, a zero is not a one. That's your life inside the computer. It's either a zero or a one. So a zero is not a one. That's simple. That's simple to think of. Zero on a ruler, right? You have zero, arguably on the left, and you have 12 on the right, and that's 12 centimeters. Convert that one, right? We got off a little bit, but you just noted there's two units of measure we use, right? European metric system has different units than what's called the SAE system, or standard units depend upon a country. So anyway, zero. 0 to 12 inches, 0 to 100 degrees Celsius, right? Freezing to boiling. 32 degrees Fahrenheit to what? 300, 200 and something degrees boiling point. So that scale kind of doesn't make a bit of sense, but it's got a lot more numbers in between freezing and boiling, so it has more granularity. Some would argue, but it's not true. So zero, what is this thing? Why is it important? So I mentioned kind of can't have zero without a one, or nothing exists. It gets into the problem of the beginning of the universe and what was nothing. So this zero idea has, let's use the word relativity, because the scales humans invented originally were relative to what we knew. Boiling water was easy and consistent. Freezing water was easy and consistent. Human body temperature, whatever, was easy and consistent. I don't know where the Fahrenheit scale came from, but, well, I do, but different story. So Fahrenheit and Celsius are both relative scales. The way you spot a relative scale is if its numbers can go negative. That is not a useful scale in science. In engineering, you'll use these references a lot, but in the sciences themselves, when you're doing measurements in physics, in calculus, in chemistry, you have to use absolute scales. A scale that starts at zero, it has no negative numbers, and it goes to infinity. There's no bounds on this, how close you can get to zero, or how far you can get to infinity. And then that's confusing, because you get into magic and mysticism out there on the boundaries at either the left or the right sides of these scales, when actually it's just unknowns. We don't know what's at zero. So what's a challenge with zero? In the pressure scale, science would typically use pascals. Pascal is an absolute pressure scale. It goes from 0 to infinity. But the challenge is we can't get to 0. How can we prove 0 on a Pascal, on an absolute scale? We can't get close to 0. 0 is something we can only theoretically touch at this point. 0 is where time started. 0 is where temperature started. 0 is where pressure started. So This zero concept is really confusing, but you have to force it back into the math and the science to speak to reality itself. To do the equations about reality itself requires these absolute scales, even though you may never get to zero. So zero was interesting. I mentioned part of my career, I had intensive training, geek level training on pressure measurements. Pressure vessels, pressure measurements for a submarine going underwater. Pressure measurements for an aircraft flying at, close to the speed of sound, above the speed of sound. How does that pressure transducer behave in a supersonic environment? These were the types of discussions we had around how precise the measurements for these different pressure measurements can be. So you've got air pressure, you've got water pressure, and then you've got a physical pressure of mass, a physical object. So even the earth itself, so air, water, and soil exert pressure. Everything in mass can exert a pressure, right? All of the elements, we're in pressure measurements now. We're trying to get a perfect vacuum, an absolute zero vacuum. We want to see if we can get our pressure gauge to read absolute zero. The challenge is when you get to that low, that close proximity to absolute zero, the vessel you're trying to create that zero in itself starts to disassociate atoms and come apart. So inside that absolute zero pressure vessel, if you could ever get there, containment is self, is dissipating, is falling apart. There's this thing, like I said, called a vapor pressure for every element that is in the periodic table and those isotopes that I speak to. So the fact is, absolute zero is an idea. It is a human developed concept that is required for physics, science, chemistry to work, yet we can't get there. We keep getting closer and closer. I mentioned that our measurement sciences are out to 23 to 25 decimal places of accuracy, of precision. And for any measurement instrument, you qualify and quantify what it measures. You qualify what type of particle it's measuring. If it's a high energy particle detector, if it's light, you qualify and quantify. You qualify exactly what type of light can it see, UVA, UVC, UV light. Can it measure that light? Is it a useful measurement? This is what some folks do. Back there in labs and lands and scientists that exist and are real. And you don't get to knock on their doors very easily. So this absolute zero is hugely important. The measurements, the scales that we have to use inside these calculations, again, if you can't speak in those absolute values, you have to convert into an absolute scale. And that's valid. It's no problem, no big deal. It's what we do is convert scales to be able to do math. It's why some of our spacecraft have gone off course, because the conversions in between those scales are confusing and challenging to coordinate. So a spacecraft piece of software might hand another piece of software what it thinks is right, but is wrong. So absolute zeros. This is maybe I'll follow on. But if someone's speaking about a flat earth, about a dome, can't speak in those absolute values or to the reasons for those absolute values, then they should really keep on trying. It goes into the denominator of an equation. In order to do long equations, there is a common denominator required. It's just rules of math. So this one was too long, got up too early, and it's skirting around the idea, the concept of absolute zeros. And infinity has the same challenge to get to. So we have invented high energy containment using magnets. That's something interesting and cool. But we don't have the physical materials to do a lot of what we're wanting to do yet. So keep trying. Molten salt, it's a long ways off. Not worth it to some books, some accounting methods.